Hi folks! The following is our second video on kinetics. I'm going to be talking about the theories related to the transition state, as well as activation parameters which describe the energy of the transition state. For experimental chemists, because the transition state is so short-lived, it can almost never be observed experimentally. So we need to figure out the relationship between things we can measure in the lab, like rates or rate constants, and relate those to the energy of the transition state. Let's consider a single starting material going on to form the product. This is a single-step reaction, and the transition state is our highest point in energy along this reaction coordinate diagram. Delta G double dagger, the Gibbs free energy of activation, is the difference in energy between the starting material and the transition state. We will consider both the rate at which the starting material goes to the transition state, which I'm labeling orange K, and we'll also consider the rate at which the transition state goes on to products. I'm going to call this yellow K double dagger. The double dagger sign is a way of denoting that something is related to the transition state. Before getting into the math, the assumption we're going to make is that the transition state is in equilibrium with the reactants. So you could think about the transition state sort of like a really high energy intermediate. You would have an equilibrium between starting material and the transition state, and the orange K is related to the rate in the forward direction. And then you can also think about an equilibrium between the transition state and the products. Here, that rate of going from the transition state to the product is defined by the rate constant K double dagger. If we wanted to look at the rate for this reaction, going from starting material to product, our rate law could be written as the rate as being equal to the rate constant K times the concentration of starting material. This is the rate at which starting material gets converted into the transition state. Alternatively, we could write this rate law as being equal to K double dagger times the concentration of the transition state. This is a rate law just looking at the second step, going from the transition state to the product. I have two different equations here, both with rate on the left side, so I'm going to set the right sides equal to one another. I would have K times the concentration of starting material equal to K double dagger times the concentration of the transition state. I'm going to separate out the concentration of the transition state term by dividing both sides by K double dagger. This gives me the concentration of the transition state as being equal to the rate constant K times the concentration of starting material divided by K double dagger. Now, instead of a rate constant, we're going to think about an equilibrium constant, since we've assumed that the transition state is in equilibrium with the reactants. So we could define an equilibrium constant, big K double dagger, for the equilibrium between starting material and the transition state. This big K double dagger would be equal to the concentration of the transition state divided by the concentration of the starting material. Like I did using the rate discussion, I'm going to separate out the concentration of the transition state term by multiplying both sides by the concentration of starting material. This gives me concentration of transition state as equal to big K double dagger times the concentration of starting material. I'm setting this up so that I have two equations where the concentration of the transition state is separated, one of them involving rate constants and one of them involving an equilibrium constant. Before we proceed, we have to think a little bit about how delta G relates to KEQ. Delta G is equal to negative RT natural log of KEQ. Or we could rewrite this so that we have KEQ equal to e to the power of negative delta G over RT. If we're looking at an equilibrium between the starting material and the transition state, this is an equilibrium constant K double dagger, and that's going to be equal to e to the negative delta G double dagger divided by RT. So like our original equilibrium constant equation, but involving a transition state instead of a product instead. I'm going to take this equation and plug it in for the big K double dagger from before. This would give me concentration of transition state as being equal to e to the negative delta G double dagger divided by RT. That whole term multiplied by the concentration of starting material. Now I have two different equations with the concentration of the transition state on the left side, so I'm going to set the right sides equal to each other. I get rate constant K times the concentration of starting material divided by the rate constant K double dagger being equal to e to the negative delta G double dagger over RT, that whole term multiplied by concentration of starting material. Here I've just rewritten that same equation from the previous page. Notice that on both sides of the equation I have a concentration of starting material term on the top. These terms will cancel, and I'm going to move K double dagger to the right side by multiplying both sides of my equation by K double dagger. This gives me an equation where I have my rate constant little k on the left as being equal to K double dagger e to the negative delta G double dagger over RT. Delta G double dagger has to do with our barrier height, but we don't yet know what K double dagger is. This term K double dagger is related to the rate of a molecular vibration, which has a rate of 10 to the 13th per second. Don't ask me about the math here, but this K double dagger term is equal to Kb, the Boltzmann constant, divided by a constant h times the temperature. Kb, the Boltzmann constant, is 1.38 times 10 to the negative 23rd joules per Kelvin. H is Planck's constant, 6.626 times 10 to the negative 34th joules per second. And always make sure that your temperature is in Kelvin. If I plug this equation for K double dagger into my equation from before, I get the following equation, which is known as the Eyring equation. This equation is looking at our rate as a function of temperature. And this is related to our delta G double dagger, or our barrier height. We have an observable rate constant on the left, something we could measure in the lab. Delta G double dagger is our barrier height. And we have two temperature terms, one before the exponential and another one in the exponential term. We're going to keep going with this to get to something that is going to be more graphable. So I've rewritten the same Eyring equation from before, and what we're going to do is look at the delta G double dagger term and separate it out into entropy and enthalpy terms. Delta G double dagger is related to these two terms by the equation delta G double dagger is equal to delta H double dagger minus T delta S double dagger. This is the transition state form of our familiar delta G equation. I'm going to substitute in the right side of this equation for the delta G double dagger term in my Eyring equation. This would give me the rate constant k as being equal to, my pre-exponential term is the same, but now it's e to the negative of delta h minus t delta s divided by RT, with both delta h and delta s being double dagger terms. I'm going to tidy up my exponential a bit by separating out my two terms. It'll be e to the negative delta h double dagger divided by RT plus delta s double dagger divided by R. Notice that for my entropy term, the temperature on the top and the temperature on the bottom canceled, and the negative of a negative is a positive. What I'm going to do next is take the natural log of both sides of this equation. This gives me the natural log of k being equal to the natural log of kb over h times t, and then now everything that was in the exponential is just in normal form. So I have negative delta h double dagger divided by RT plus delta s double dagger divided by R. To move my natural log of kb over h times t to the other side, I'm going to subtract this from both sides. On the left, I now have my two natural log terms, and then now all that's left on the right is minus delta h double dagger over RT plus delta s double dagger divided by R. We can rearrange natural logs using the following rule, where if you have natural log of x minus natural log of y, that's equal to the natural log of x divided by y. We would take our rate constant k divided by kb divided by h times t, and we can rewrite that whole term as natural log of rate constant k times h divided by the Boltzmann constant kb times t on the bottom. Then on the right-hand side, everything is roughly the same. I've just pulled out the temperature term. All of this rearranging gets me to a form of my equation that is of the type y equals mx plus b. So in a worksheet problem or an exam problem, I wouldn't ask you to derive these equations, but I wanted you to see the math behind it. For some people, depending on your area of chemistry, it may be important to know the math behind it. But I want everybody to know a few takeaways from the derivation I showed. Our assumption, in order to get the Eyring equation relating the rate constant and the barrier height and temperature, we assumed that the transition state was in equilibrium with the reactants. Then we assumed that the rate constant k double dagger was as fast as a molecular vibration. What this means is that once you've reached the transition state, it is extremely rapid to go on to product. Then I want you to be familiar with and be able to use the two forms of the Eyring equation that I defined. And it's the second of these that we're going to use more readily in Eyring plots, which I'm just about to discuss. Here I've rewritten the form of the Eyring equation where I have the type y equals mx plus b. What we would do is consider a graph where we have our y-axis as the natural log of rate constant k times h divided by kbt, and the x-axis is going to be 1 over the temperature. What we would do is measure rate constants in the lab at different temperatures. Then we would convert into these x and y axes and plot the data. We would then fit this data to a line. The slope of the line is equal to negative delta H double dagger divided by R. And then the intercept is equal to delta S double dagger divided by R. You would get the data for this plot by measuring rate constants in the lab at different temperatures. You would look for the appearance of product or the disappearance of starting material by spectroscopy like NMR or IR. You want at least 5 data points ideally, and you want at least a 30 degree Kelvin temperature range. Similar to the Van 't Hoff plot as well, because you're extrapolating all the way back to the y-axis to get your entropy term, this term is more error-prone than the enthalpy term. And while the Eyring plot doesn't give you delta G double dagger directly, you could solve for it, usually done at 298 Kelvin, using your delta H double dagger and delta S double dagger values that you derived from the Eyring plot. I want to talk a little bit more about our delta G double dagger, delta H double dagger, and delta S double dagger terms. These are collectively known as activation parameters. So far I've only talked about how these terms would work out for a reaction involving a single step. It's more complicated for a multi-step reaction because all of the steps up to and including the rate determining step, will contribute to these activation parameters. If this is the case, your delta H double dagger and delta S double dagger are a composite of the 2 separate steps, sort of amalgamated into a single term. So let's consider the following reaction coordinate diagram, where I have a second step that is rate determining. In the lab, I would determine rate constants at different temperatures and plot them using an Eyring plot to get delta H double dagger, delta S double dagger, and delta G double dagger. The values I measure in the lab take into account both the first and the second steps of this reaction because the second step is rate determining. A takeaway is that it's going to be easiest to interpret these activation parameters for a single-step reaction, though it's not impossible for multi-step ones. I want to discuss how we would interpret the delta H double dagger term, known as the enthalpy of activation. This term gives us information about how the enthalpy of the starting materials compares to the enthalpy of the transition state. At the transition state, you'll commonly see some bonds partially broken. And usually, bonds are more broken at the transition state than they are formed. This means that the enthalpy of activation term is almost always positive, indicating that this term is endothermic. This is because it takes energy to break bonds. So almost always expect for delta H double dagger to be positive. In contrast, our entropy term, delta S double dagger, known as the entropy of activation, this one could be positive or negative. This term tells us about how ordered the transition state is compared to how ordered the reactants are. Here as well, since we're just thinking about kinetics, we're only thinking about the starting materials in the transition state, not the product at all. If at the transition state you've lost degrees of freedom, delta S double dagger will be negative. Often this will imply that you had 2 molecules coming together in a transition state. And if you have degrees of freedom being gained at the transition state, this entropy of activation term will be positive instead. You could see this if you're opening up a ring, or if you have 2 molecules forming from one starting material molecule. I'll show you some examples of entropies of activation to give you a sense for what these values will look like. As a first reaction, let's consider a loss of a leaving group from an alkyl halide. I have a carbon-chlorine bond breaking to form a carbocation and a chloride anion. This is a reaction that takes one molecule and forms two molecules, and at the transition state, my carbon-chlorine bond is partially broken. I have a developing positive charge on carbon, denoted as a partial positive charge, and developing negative charge on chlorine, written as partial negative. We would predict that this would be a positive value because at the transition state, our molecules are coming apart, and when you have two molecules, you have more degrees of freedom compared to one. They're not totally separated at the transition state, but they're more separated than they were in the starting material. Now let's consider a radical reaction where we have ROOR, also known as ROR, and the oxygen-oxygen bond is breaking homolytically. This forms two equivalents of RO radical. At the transition state, my oxygen-oxygen bond is breaking, and my radical character at each oxygen is developing. I could denote this not as a partial charge, but as a partial radical character. Although it's a different reaction than my first case, this is another example where I have one starting material going to two products. As this oxygen-oxygen bond weakens, I have more degrees of freedom at the transition state relative to the starting material, so my delta S double dagger term is positive as well. In this case, a very similar value of plus 11 EU. Now let's consider a substitution reaction going by an SN2 mechanism. I have a cyanide nucleophile attacking a methyl iodide molecule, where I have carbon-carbon bond formation and iodide serving as the leaving group. At the transition state, I have a carbon-carbon bond forming and a carbon-iodine bond breaking. The nucleophile comes in directly opposite my iodide leaving group. Because the nucleophile needs to come into this very specific site opposite the leaving group, we would call this transition state highly ordered. Like the molecules had to come together in exactly the right orientation in order for this reaction to proceed. And also notice that at the transition state, this looks like one molecule rather than two molecules. Going from two molecules to one, and especially one that's highly ordered, is not favorable entropically. This gives me a large and negative delta S double dagger value of negative 30 EU. Typically, we'll see values that appear at or between negative 30 EU and plus 10 EU. Our large negative values will be for transition states that have a lot of order or bringing multiple molecules together in the transition state, while entropically favorable transition states will have positive values, no larger than 10 usually. I want to end by talking about how we would interpret the delta G double dagger term. This is known as the Gibbs energy of activation or the Gibbs free energy of activation. A useful rule of thumb to keep in mind is that a unimolecular reaction that is occurring at a rate that would be convenient for somebody to measure in the lab would have a delta G double dagger of about positive 23 kilocalories per mole. I want to show you some examples of different delta G double dagger values. We're going to look at 3, 10, 23, and 30, and I'll show you what rate constants and half-lives would look like for those delta G double dagger values. Using the Eyring equation, you can convert a delta G double dagger value of 3 kilocalories per mole at room temperature, 298 Kelvin, to a rate constant of 4 times 10 to the power of 10, with units of per second. This corresponds to an extremely short half-life of 17 picoseconds. This would be exceptionally rare, and I can't think of an organic reaction with an overall rate this fast. Increasing the free energy of activation to 10, the rate constant drops. Now it's 3 times 10 to the 5th power, but this still corresponds to a very fast reaction, having a half-life of 2 microseconds. Our more typical value for a reaction that would be run at room temperature is the delta G double dagger of 23. This rate constant would look like 8 times 10 to the negative 5th power, and it would have a half-life of a little over 2 hours at room temperature. Going from the free energy of activation of 23 just to 30 causes the rate constant to drop significantly. Now it's down to 6 times 10 to the negative 10th power. And this would correspond to a half-life of 35 years. So it's not that you can't run a reaction with a delta G double dagger value of 30, it's just that you would want to run it at higher temperatures instead to make it go faster. In summary, today's video talked about the transition state and theories related to it that allowed us to derive the Eyring equation, which relates a rate constant to the free energy of activation as well as the temperature. And I've also talked about how we interpret activation parameters. That's it for this video. I will see you in class.